Hi, today's lesson is on heat and specific heat. Oh wow. Hopefully you can remember a time when you've been to a beautiful beach like this on a nice warm sunny day, and perhaps you were barefoot and you might have noticed that the sand was really hot. And then when you got down to the lake or the ocean, the water was really cold. And maybe if you walked on some grass, it was not quite as hot as the sand or not quite as cold as the lake or the ocean. And you notice this. And that's because even though it was on the same day and the temperature of the air that was hitting the sand and hitting the water and hitting the grass was all the same temperature, the materials did not heat up the same way. So today we're going to talk about why that is so. So what makes some substances heat up very quickly or some heat up slowly? So that's our discussion for today. So what are those factors that affect how much heat is needed to heat something up or how much heat is given off when something cools down? Well, here are some of the factors. One, the mass of the material matters, and you know this. If you take a pot of water and you half fill the pot with water and you heat it on the stove, and you take the same pot and fill it all the way to the top with water and you put it on the stove, it takes a lot longer to heat up the full pot than it does the pot that's only half full. And that's because the amount of material you're going to heat up matters to how much heat you have to add. You have to add more heat if you have more material. So the mass of the material matters. Another factor that matters is how much do you want to raise the temperature? Do you want the temperature of your material to go up 1 or 2 degrees or 10 degrees or 30 degrees? So the amount of the material changes in temperature matters. If you want it to go up more degrees, then you have to supply more heat or more energy. Another thing that matters is, from our example of the beach, the type of material matters. Not all material heats up the same way. Some take a lot of energy to heat up and some take very little energy to heat up. We call the energy that's needed to heat up a material the material's specific heat, and it's given a small letter C. Just like mass was M and change in temperature was that triangle T, which is delta T, specific heat is given the letter C. And it's defined as the amount of heat needed to raise 1 gram of material, or sometimes 1 mole of a material, 1 Kelvin or 1 degree Celsius. And it varies for different materials. And it also varies for the different states of those materials. So water has a different amount of energy needed to heat up if it's a liquid compared to if it's a gas or ice as a solid. And the specific heat has units such as, and notice these units are 3 units. So joules per gram degree Celsius, or joules per mole Kelvin, or calories per gram degree Celsius, or kilojoules per gram degree Celsius. So on the top it has some energy unit such as joules or calories or kilojoules or kilocalories. And the bottom it has something to do with the mass of the material or the amount of the material and the amount of temperature that you're raising it, which is 1 degree. So now here's a table that contains specific heats of several different types of material. And let's take a look at them. You notice water, which is near the bottom, has a pretty high specific heat. What does that mean? It means it takes a lot of energy to change the temperature of water, the same amount of degrees as it does maybe a gold or silver. Notice many things that are metals have very low specific heats. And you should know that from experience. We often cook with pots made of metals. Why? Because they heat up very quickly. You will also notice at the bottom some non-metals. We have granite and glass, and they have some moderate specific heats. And ice a little bit lower than water, about half water. And so these are some examples of the specific heats of materials that you might be using. So, what kind of problems might you have to solve? What if you needed to calculate the heat involved in heating up a substance? So, let's take an example. To calculate how much energy is used to heat up a substance, you need the mass of the material. You need the specific heat of the substance. You need how much change in temperature the substance is going to undergo. And then this is the equation you're going to use. So Q stands for heat. Why Q? I don't know, but Q stands for heat. Equals the mass times the specific heat times the change in temperature. So if you double the mass, it's going to take twice as much heat. If you want twice as much temperature change, it's also going to take twice as much heat. And it's going to matter the material because that's going to affect the C value. If it's going to be a high heat value for water because the specific heat of water is high, or something low like lead. So, and this equation works for solids, liquids, and gases, but you have to use the right C value. So C is not only specific heat, but it's also specific for the material and the state of the material. So the C value for water when it's a liquid is 4.184 joules per gram degree Celsius, but the C value for ice, water when it's a solid, is only 2.09 joules per gram degree Celsius. And we'll talk about later why the difference between the liquid and the solid state. So let's try some problems. Here's a question. How much energy is used to heat 100 grams of ice? So now we're going to start with solid water, and we want to heat it from 10 degrees below zero, minus 10 degrees Celsius, to 0 degrees Celsius. Now notice here it says minus 0 degrees Celsius. That's a true definition of a pessimist. It shouldn't say minus there. I'm not sure why that is there. The specific heat of water as a solid is 2.09. It takes 2.09 joules of energy to heat up 1 gram of water 1 degree Celsius. So there's the equation we're going to use. So the first thing is you're going to write the equation. Then you're going to substitute for the values. So for mass, the mass was 100 grams. The specific heat was 2.09 joules per gram degree Celsius. And the change in temperature going from minus 10 to 0 is 10 degrees Celsius. And then we just multiply them together, so really simple math. And I get 2,090 joules. If I wanted to, I could change that to 2.09 kilojoules, because that's kind of a big number. And let's look, we need 3 significant figures, and that's what we have. So there you have it. A little information about heat, why the sand gets hot and the water's still cool, and how to solve problems involving heat. So thanks for listening.